Speaker is Professor Jong-Hae Keum from KIAS. He will speak about Q-Homology projective planes.
Thank you very much for the introduction. I'm very impressed with this facility. I really like to see the ideal status after a few months, completion of this construction of this facility. But anyway, today I'd like to talk about this Q-Homology projective planes. Well, I prepared some slides. Actually, I hate slides, but I had watching slide learning very fast, so I go very slowly. And also, I work on board. So, Q-Homology projective planes means normal projective surfaces with minimum possible Betti numbers. So here, the outlines, Q-Homology projective planes, definitions and examples, and the maximum number of quotient singularities on Q-Homology projective planes, and Montgomery-Young problem. This is originated from differential topology, circle action on 5-dimensional sphere, an algebraic version of Montgomery-Young problem, and progress on algebraic Montgomery-Young problem. And then I will pay attention to Gorenstein case, and few remarks on symplectic case and in positive characteristic case. So here is the definition. Okay, we will work on the complex number field. Well, some of these definitions can be extended to positive characteristic, but here is the definition. A normal projective surface S is called a Q-homology P2 if it has the same Betti number, so rational homology groups as P2 for all I, meaning that first Betti number S and third Betti number 0 and second Betti number is equal to 1. If S is smooth, then we have P2 or fake projective plane. See, if S is smooth, the second Betti number is 1, so Picard number is equal to 1. This means smooth, and then S is smooth. So the PG, second Betti number 1 and first Betti number 0, so irregularity should be 0. Yeah, I'm following the notion by Professor Mendez-Lopez yesterday, and geometry genus also 0. So this is equal to peak object, peak of X. So here the canonical class contained, and we know C2 Euler characteristic of X is 3. So kx squared is equal to 9 by method formula. So we have two choices. Kx is ample or Kx is negative ample. Yeah, Kx negative ample is X is P2, and in this case X is a fake projective plane. It's a surface of general type. Minimal Well, fake projective planes that recently classified more precisely, their fundamental groups are classified. By and Psyche Jung, and the two more group theorists, Cartwright and Steger, Tim Steger. So there are 50 possible fundamental groups. These fundamental groups are all subgroup of PU21. In this case, they are all Ball quotient. So fake projective plane is always Ball quotient. Two-dimensional ball, Basel a fundamental group. It's co-compact arithmetic. Acting freely on B2, and whose co-volume is 3. And each fundamental group corresponds to a pair of they are mutually conjugate. So if you change the complex structure by taking complex conjugation, then you get a different fake projective plane, the same fundamental group. So we have exactly 100 fake projective planes. Well, number is too good, but now I believe. Well, the Prasad and Young, they give the the process for classification of such fundamental groups, and then actual computation done by these two people using computer. So this result is obtained by computer. So they actually compute all possible subgroups. Well, beforehand, there are a list of maximal arithmetic subgroups. There were a list of maximal arithmetic subgroups. So and then any fundamental group, if occur, then it must be a subgroup of one of these maximal arithmetic subgroups. So they check all possible such subgroups, which gives you correct quotient. Like so that the first Betti number should be 0, and the second Betti number should be 1. Okay, so but we have rather satisfactory classification of fundamental groups of fake projective planes, but we still do not know any single example in projective geometric way. The defining equation or whatever or I mean, quotient of known surface or covering of known surface. So still kind of algebraic geometric point of view, so still somehow these surfaces should be studied. Okay, and then the next case you can think of, okay, you can impose just the singularities of simplest type. For example, only A1 or A2 singularities, say. So A1 is order 2, A2 is order 3, both are rational double points. In this case, you can actually prove that we have these cases, one of these cases. S has only one A1 singularity or one A1 plus one A2 singularity or 3A2 or 4A2. So in these first two cases, it must be rational. So this is nothing but the singular quadratic. And these two cases, it could be rational or also quotient of fake projective plane. So there are many fake projective planes having automorphism order 3, and then any such quotient should have 3A2 singularities. And also this is a surface of general type, having k square is equal to 3. And in this case, also this surface of general type, having k square is equal to 1. So actually one can show that in this case, the S cannot be general type. And also in this case, also S cannot be general type. These both follow from Obifold version of Bogomolov-Miyako-Yau inequality, I mean, log version of Miyako-Yau inequality, which was explained by Marius, Professor Koras. So for example, if A1, S has 1A1, then k square, 1A1, then so prime, this minimal resolution. Then second Betti number S prime is equal to 2, 1 plus 1, here 1, so you have one exceptional curve. So this is 2. So KS prime square is equal to 8 by Nessa formula. But on the other hand, what's so-called E Obifold Euler number, this is nothing but, well, this is in Professor Koras' terminology, this is nothing but I'm sorry, this is equal to, in this case, this is rational double point, so this is equal to this, and Ks square is nothing but Ks plus D sharp prime plus D sharp square. In this case, this is equal to 0. And E Obifold, this is just Euler number of S minus sigma 1 minus the local fundamental group at each point P. At each point P. This is not a good notation, but this way. So in this case, you see this Euler number is 3. And we have only one quotient singularity of order 2, so this is 1/2. This is 7/2. So, but 8 is not smaller than. Oh, this is 5. Sorry. So you can easily. This is another application of this homomorphi하고 양원 inequality. So this says, the KS cannot be NF. In other words, KS prime is not NF. So it cannot be a general type, so you can show that S prime is rational. Eventually, it's equal to only one singular quadratic. Okay, so here's a small remark. Any cubic surface with 3A2 is isomorphic to this surface. This surface has three A2 singularities on coordinate points. And if a Q-homology P2 has rational singularities only, then its minimal resolution has geometric genus irregularity 0. In this talk, I will restrict myself to the case with only quotient singularities. So now SS at worst quotient singularities. Yeah, of course. Yeah. Contraction of kind of elliptic configuration. So here, I mean, you can define arbitrary. Yeah. So this definition, I mean, you can go. Usually, sometimes kind of you impose from the beginning, S has only quotient singularity. But so in general, you can define for any normal projective surface, define this notion. So under this assumption, S is a Q-homology P2 only if second Betti number is equal to 1. So in this case, first Betti number automatically 0. Yeah, if first Betti number is non-zero, then you can think of Albanese map. Yeah. So maybe you take the minimal resolution first, and then you have an Albanese map from the minimal resolution to abelian variety. And then if this is a fibration, then the Picard number at least 2 violating. And this is rational anyway. The quotient singularity is rational singularity, so all singularities lie on fiber. So the second Betti number 1, the second Betti number at least 2. Or if not, it's Albanese dimension is 2, then still you can have some positive PG. Okay, so now we have so here the second Betti number 1. So Picard group has rank 1. Picard number is equal to 1. So we have trichotomy here. Canonical class ample, or canonical class negative ample, or canonical class numerically trivial. So let's be such a Q-homology P2 with quotient singularities, and S prime be a minimal resolution. If negative ample case, and this is nothing but low del Pezzo surfaces of Picard number 1. And in this case, there are plenty of examples, all weighted project planes, and any quotient of P2 by a finite group. In this case, this surface, minimal resolution has Godard dimension negative infinity. So this is a rational surface. And numerically trivial, getting more interesting. And these are called log Enrique surfaces of Picard number 1. And this example can be obtained from a rational surface or Enrique surface. Yeah? So you contract, for example, suppose an Enrique surface contains 9 smooth rational curves with certain AD configuration. then you can contract them to give you rational double points. In this case, NK surface at picard number 10. So after you contract 9 curves, you have picard number 1. So this gives you one such example. And in this case, always, if such an example is coming from NK surface, then always it has rational double point. But also you can, for example, start with rational surface and blow up suitable way, and then contract same number of curves as the number of blow-ups. Then you get picard number 1 or second Betti number 1 in this case. And the last case is general, I should say, as a sample. In this case, the example is quotient of fake projective planes, or contraction of a suitable blow-up P2, so suitable blow-up and suitable contraction, or suitable blow-up NK and then suitable contraction. So in this way, also that Godard dimension 1 and general type. So the minimal resolution S prime has Godard dimension negative infinity, 0, 1, 2, all possible values. So in this case, it's much more general, but the problem is that in this case, it's pretty difficult to find examples. So this is one of the difficulty in classification theory of algebraic surfaces. So general case is pretty difficult to find examples. Here, the problem reposed by Shkola, classify all Q-Homology P2 with quotient singularities. Well, this problem is originally related to a Montgomery-Young problem. Okay, so the first question is maximum number of quotient singularities. Are there any bound for the number of quotient singularities? Let this be a Q-Homology P2 with quotient singularities. And first question is how many singular points on S? Well, this question can be successfully answered by this Bogomolov-Yau inequality. So this number is bounded by 5 by the obifold Bogomolov-Yau inequality, or log version of BMY. So here I use obifold because I assume only quotient singularities. So this is obifold surface. I'll give you the proof later, very quick. And then many examples with at most 4 singular points, all found by a topologist, Branton, and long been conjectured that this should be the bound. And the Losov proved that low del Peggio case, the number is bounded by 4. And jointly with Dongsun Huang, my former student sitting in the audience, we have classified this with 5 singular points. These examples are all coming from NK surfaces. Here is the more precise statement. Let S be a Q-homology P2 with quotient singularities. Then number of singular points is bounded by 4, except the following case. This is the case, exceptional case. S has 5 singular points of type 3A1 plus 2A3, meaning that 3 singular points of type A1 and 2 singular points of type A3 all happen to be rational double points, but here we just quotient singularities. And its minimal resolution is an NK surface. So NK surface is an algebraic surface, always algebraic. It's PG equal Q equal 0. And fundamental group is cycling of order 2 and Godard dimension 0. So one of the class and the for algebraic surface is Godard dimension 0. Always the universal cover is K3 surface. And now you can think of integral homology P2. This is nothing but the same integral homology as P2. So rational homology and integral, the difference is that the torsions, You take rational homology, then all torsions will be killed. But integral homology, you have torsions. So this means that such an object shouldn't have any torsion. With quotient singularities at most 4 singular points. Well, every integral homology is a rational homology P2. So, but this exceptional case all coming from NK surface, but NK surface has 2 torsion. So once you contract 9 smooth rational curves of Dynkin type, 3A1 plus 2A3, these are still rational singularity. So it doesn't change the torsion. It doesn't change the fundamental group. So still, the surface S has fundamental group cycling over the 2, or the first homology group, or first integral homology group cycling over the 2. So it is not integral homology P2. So here, every G cohomology P2, integral cohomology, here cohomology means it has isomorphic cohomology ring. So here homology means just each dimension we have the isomorphic space, but cohomology means that, that the cohomology is a cohomology ring. That the ring structure should be isomorphic. So integral cohomology P2 with quotient singularity has at most 1 singular point. And if it has 1, then the singularity must be of type E8. And then why not rational cohomology P2? Well, in this case, it's nothing but there are Q-homology. Well, just here, and here, as long as the intersection form is non-degenerate, then any Q-homology P2 is a Q cohomology P2. So in this case, only the non-degeneracy is the matter. So here, just a final remark here. There are Q-homology P2 with arbitrarily many rational singularities. So if we allow S to have a rational singularities, then we cannot bound the number of singularities. Also, the problem would be kind of infinite. Here's an example. You take a rational ruled surface, Hilbert surface, with negative section, so sigma V, say. So you take one, and then you take arbitrarily many, sufficiently many K rulings, K fibers. And then you take blow up twice so that each becomes like this. So and then you contract, so you blow up 2K times, and then you contract all these -2 curves, and then you contract this bunch. So if sufficiently large, then these rational singularities. So in this way, you can construct arbitrarily many example. An example with arbitrarily many rational singularities. Okay, so here's the proof. So to do, here we use this Bogomolov Yao inequality, obifold version of BMI inequality. So here is the obifold Euler number. This is nothing but the right-hand side, what Professor Koras wrote. But this is only, so we don't, here, no minimal resolution appear here. So everything on the singular surface. So here, this is the local fundamental group, the order of local fundamental group at each singular point. And this is the BMI inequality. Well, the original, for smooth case, the original the inequality was proved by Bogomolov, so with 4, and then Miyaoka Yao independently, different method, improved this 3. And then the singular version, the obifold version, is proved by many people, contributed. So Nakamura is one of them. Okay, so here anyway, so this obifold, in this case, this is a rational number. So now we have an intersection on the singular surface. So this is a rational number. This is nothing but, as Professor Koras mentioned, this. Okay. It's nothing but S prime plus. So D lives on the exceptional. Lives on the curves which are contracted. It's a rational divisor. So this is a rational number, and also this is a rational number. So the only assumption is that KS is NAP. So this is exactly the same. So yeah, the smooth case also we need this KS is NAP, the napness of KS. So certainly this is not true. It doesn't hold for ruled surface. So in this case, this is non-negative. So corollary is that this number is always non-negative. So this is non-negative. So this already bound the number of singularities. So here, this another version, in the case when a negative KS is NAP. In this case, this is non-negative. So in any case, we have this obifold Euler number is non-negative. So proof. So here, let me give you one proof of y is bounded by 5. So let me go up here. So this is the formula. So bigger than the obifold is so this is 3, and this number is at least 1/2. Yeah. So this implies the number of singular points is at most 6, and if this is equal to 6, then all are order 2, so 6A1 singularities. Okay. So we have to get rid of this case. And then you can think of S tilde, S prime to S. And then the second Betti number of S prime is equal to 1 plus 6 is 7. So KS prime square is equal to 3. So that the KS prime and the exceptional curves, 6 exceptional curves, they generate a sublattice inside free part. But this is nothing but the lattice 3 direct sum minus 2 to the 6. Yeah. And you see, this is unimodular. By Poincare duality. So this is over lattice, same rank 7, same rank. So it must be, so this one should have discriminant square number, but this is not square number. Yeah. So this discriminant and determinant. Square. This is contradiction. So you can assume that the number of singular points at most 5. So, and then okay, we proceed. One can proceed the classification of such case, and enumerate all possible 5 tuples of orders of local fundamental groups using the Baumol-Biaoka-Yau inequality, and then we have only this short list, but it's not quite short, and these are only finitely many. The number Q, the last order, the fifth singularity, the order is 3, 4, 5, 6. So 1, 2, 3, 4, 5, 6. So it's a 6 sporadic case, but this is a kind of infinite series for any Q. So the problem is how to reduce this case. The first reduction step is the fifth singularity of the case, first case. It must be of type T6, the singularity of class T, if cyclic, of type D5 if non-cyclic. Yeah, singularity of type T6, these singularities are studied by Loyenga and Wall, and then Kola and Shepard-Baron. Well, these are quotient singularities which have Q-Gorenstein smoothing. Yeah? It has a smoothing such that the total space is Q-Gorenstein. Also, of course, rational double points has Q-Gorenstein smoothing. So these are other than rational double points. The class T is different from rational double point. So these are singularities of this type. The order is 6n square and 1, 6na minus 1. So I'm using the notation given by Professor Miles Reed. So here, n is any number, and a is any number coprime to n. So the kind of smallest possible, of course, there are two. One is if you take, okay, there are, of course, the class 6 means, yeah, type T6 means here 6. Okay. So but for various number n and various number a satisfying this, all such singularity can be obtained from this. So that the smallest one is this. This is a string. The minimal resolution Hirzebruch-Jung string consists of 6 smooth rational curves, -3 curve and -2, -2, -2, -2, and -3, forming a string. And then if you move up, going up n or taking different a, then this number becomes like this. So the string of 7, then you put here 2, and then you increase this number by 1. Or when you put 2, you increase this number by 1. And you increase this number by 1, and you put 2 here. So in this way, you can get all such singularities. So all these singularities, this is complete list for this type of singularities. And then second step, and the lattice, 4 copies of A1, and the number, the lattice generated by exceptional curves of resolution of a T6 singularity. So that the length could be arbitrary. Anyway, this sublattice cannot be embedded into a unimodular lattice. This is cohomology lattice of minimal resolution. One can show that this by induction. And also we use the local global principle and induction on the length of T6. So we can get rid of this infinite series. So we are very happy. And 2 cases left over. And then also you can get rid of some other cases. And this is another, so the first case, 2222Q. So it's a non-cyclic case. Yeah, and 2244. And in this case, one can rule out this case again, exclude first case using some geometric argument. So anyway, this is a rational double point. So its minimal resolution must be Anyke surface. And then this Anyke surface must have configuration 9 smooth rational curves of thinking type 4A1 plus D5. And then the K3 curve of S prime has configuration of 8A1 plus 2 copies of D5. Yeah, so every smooth rational curve has a disjoint pre-image on K3. So you have this. And then these 8 smooth rational curves is 2 divisible. So this is not always true for any given K3. So here S prime is an Anyke. On the K3, so here you have 4A1 plus D5. You have 8A1 plus 2 copies of D5. I mean, 18 smooth rational curves forming this thinking diagram. And then show that this is 2 divisible. In general, this is not true. I mean, K3 surface with 8 mutually disjoint smooth rational curves that which are not 2 divisible. The sum or partial sum is not 2 divisible. So I mean, any partial sum of these 8 smooth rational curves is not a multiple of other divisor. And then you can take a double cover. You can take this another K3 branched along, branched along these 8 smooth rational curves. And this another K3 which contains 4 copies of D5. Yeah, but this is already impossible. So because the Picard number of K3 is at most 20, but you have negative definite. So, but we start with projective surface. So this is projective. Yeah, it's this projective. Algebraic K3. So you can rule out this case. And then finally, this last case is supported by an example. Finally, construct an example of this type. And there is an Anyke surface with elliptic fibration with 4 reducible fibers of type I2, I2, I4, I4. Then actually the 1, 2, 1, 2, 1, 4, 1, 4, type 1, according to Kodaira notation, Well, some of these could be multiple. So NK surface has two multiple fibers, multiplicity 2. So this could be a multiple fiber. But anyway, there is a two section that intersect only one component of each fiber. So away from this two section, then there are A1, A1, A3, A3, and then this section itself gives you A1. So this altogether 3A1 plus 2A3. And now we know that any such example must be coming from NK surface with this elliptic vibration. This is recently proved by Matthias Schett. Okay, I'll go later, maybe tomorrow, on the Gorenstein case. Here, today, let me finish with this section, Montgomery-Young problem. So smooth circle action on m-dimensional sphere. So smooth circle action, so that the S1, the group, is a subgroup of diffeomorphisms of Sm. The identity elements act identically. So this is the circle itself is a group. And then so this group structure compatible with this composition as an automorphism of a diffeomorphism of Sm. Here smooth section means C-infinity action. And then each diffeomorphism of S1 is homotopic to the identity. So by Lefschetz fixed point formula, the fixed locus, Euler number of fixed locus is equal to fixed locus of Euler number of fixed locus of identity automorphism, which is whole space. And this is equal to 2 if M is even. If this is equal to 0, M is odd. So if M is even, then this is 2, meaning that fixed locus is non-empty. So we are not quite interested in this case. So if M is even, then this number is equal to 2, and such an action has a fixed point. So the foliation by circles degenerate. So here's the picture. If M is equal to 2, so this is S2. So you have, for example, foliation. So the circle action means kind of you have a foliation by circles. With this topological circle, you could be kind of curving circles, whatever. And then eventually, if you draw, then there are 2 points are fixed. Yeah, so this kind of degenerate orbit. So this not interesting case. So we assume that M is odd. And then we assume, so we are interested in the case where all orbits are circles. All orbits are circles, no point, not a point. So the C-infinity action of S1 on odd dimensional sphere is called a pseudo-free circle action if it is free except for finitely many orbits. So each orbit is a circle, but it is free for finitely many orbits. So for general orbit, the circle rotates just once, but for special orbits, the circle rotates more than once, twice or 3 times. So here, in finitely many orbits, and each of these orbits has isotropy group, a cyclic group of A1, AK. So yeah, this means that the circle action rotates the orbit A1 times, and this AK times. And also you can reduce to the case that each of these orders are pairwise prime. So this is the pseudo-free circle action. And then the problem is that how to classify this. Here is a typical example. It's nothing but the weighted projective space. So this example is a linear actions. So you embed this odd-dimensional sphere inside n-dimensional complex space. And then you also embed this circle inside C as a unit circle. And then your action is give this action by this form. Okay? Lambda to the A1, Z1, this coordinate of S to n minus 1. And the point here, A1 through AN are pairwise prime. And then you see each coordinate point, 1, 0, 0, 0, 0, you have, so the 1, 0, 0, 0, 0 goes lambda to the A1 times 0, 0, 0. So as a lambda rotate circle, then this one rotates the circle A1 times. So this gives you exceptional orbit. So in this way, you see the number of exceptional orbits are exactly those corresponding to this mean bigger than 1. So if A1 is bigger than 1, then this gives you exceptional orbit. So at most n exceptional orbits here. Well, this is called a linear action case. But actually, the action is not linear, but it's a kind of diagonal action. And in this linear case, the orbifold space, and the orbifold, I should put S1 over here, S1 slash. Anyway, so this is nothing but the weighted projective space. So basically, the classification of pseudo-free circle action on S2n minus 1 is nothing but how to measure your action far from this standard example. So the orbit of ith coordinate point is an exceptional orbit if and only if AI is bigger than or equal to 2. So, and also you can check that the orbit of a non-coordinate point. So if at least two coordinates are non-zero, then in this case, it is not exceptional orbit. So in this way, this section has at most n exceptional orbits. So this last lead to a kind of conjecture or question that any such pseudo-free circle action has at most n exceptional orbits. Maybe this is the first step toward classification of such actions. Well, it's a remark. The quotient map is a Seifert vibration. So each fiber is a circle. And there are multiple fibers, correct? Yeah, all coming from these exceptional orbits. And the base is a complex space with singularity. This is the definition of Seifert vibration. A topological manifold and this complex space, fiber is circle. And for n is equal to 2, this is nothing but a Seifert vibration. Seifert, a long time ago, showed that each pseudo-free circle action is linear, and then my standard example, I mean, and hence has at most 2 exceptional orbits. And then, not much progress until Montgomery Young, both topologists, for n is equal to 4, this is a circle action on 7-dimensional sphere. In this case, given arbitrary collection of pairwise prime, positive integers, there is a pseudo-free circle action on a homotopy S7, whose exceptional orbits have exactly those orders. So there is no bound. So the original question does not hold here. So higher dimensional case is much more complicated. And then, later, Petrie generalized this construction. Actually, they constructed, given this, and then they glued together local construction and then glued together to make a a homotopy S7. So this generalizes even higher dimensional in higher dimensions. And then this is a conjecture that so that NEC equal to 3 case is left over. And in this case, this Fintuchel and Stern, they conjecture that it has still true, I mean, at most 3 exceptional orbits. So a pseudo-free circulation on 5-dimensional sphere has at most 3 exceptional orbits. Well, this problem is wide open. Well, Stern and Fintuchel, or Fintuchel and Stern, they announced one. They withdrew their paper. This is the O2 action. This is circle action. The circle is it's a subgroup of O2, orthogonal group, index 2. So this slightly bigger action. So under this action, they proved that at most 3 exceptional orbits, but it's not. There is a gap. So why so difficult in dimension 4? I mean the orbifold. The dimension of the orbifold is 4. Well, generally speaking, if dimension is big, then you have topological freedom. So you can, but dimension is small, then in some sense everything can be seen. Yeah. This is general principle in topology. Yeah. The middle dimension is always difficult. So here's a brief explanation. Pseudo-free circle actions on manifold have been studied in terms of orbit space / this way, S1 / and the orbit space of such an action is a 4-manifold with isolated singularities whose neighborhood are cones over length spaces corresponding to the exceptional orbit of the S1 action. So each exceptional orbit gives one isolated singularity. This is quotient singularity, cyclic quotient singularity. So easy to check that if X is simply connected, like S5, no. The orbit space is simply connected because this is, it is quotient of this, that this is simply connected. And then second homology, integral homology group has rank 1 and intersection matrix. And then the exceptional orbit with isotropy type cyclic group of order A has an equivariant tubular neighborhood, which may be identified. So the basic idea is this. So this is dimension 4. So suppose you have an orbit. So suppose you have an orbit. So this is an orbit. Then this orbit becomes a point here. Yeah? So this is anyway. This is a circle. So in this circle bound a disk. You pick up any disk, and then the whole disk will become a kind of sphere. You choose carefully a disk, which gives you a sphere here. So somehow, well, each exceptional orbit gives another sphere. But this is dimension 4, and these two spheres may intersect. But if dimension 7, then these two spheres, you can choose disks which do not intersect, so that you can do it locally, and then you can glue. So, but in dimension 4, this is the main difficulty why higher dimensional argument does not work in this small dimension. So there is a one-to-one correspondence between a pseudo-free circle actions on Q-homology 5 spheres. Yeah, this Q-homology 5 sphere means 5-dimensional manifold which have the same same Betti number as 5-dimensional sphere S5 with no torsion. First integral homology is trivial. And compact differentiable for manifold M with boundary. So this is something that the candidate for the orbifold, except the singularities. So each boundary corresponds to a singularity. So boundary consists of disjoint union of length spaces. So near each singularity, this is cyclic quotient singularity. So that each near the singularity, it looks like a cone over length space, three-dimensional sphere modulo a cyclic group. So this AI is a pairwise prime, and M, this manifold with boundary, as trivial integral first homology, and integral second homology is infinite cyclic. So any such pseudo-free circle action, you can get such compact manifold by taking quotient in orbifold, and conversely, given any such M satisfying this, you can get circle action. And furthermore, such sigma is different to S5 if and only if M is simply connected. So the classification of this and classification of this is equivalent. So let me, so let me find it. So final minutes. So this, what is algebraic Montgomery-Young problem? We are, after all, we are algebraic geometers. Forget about this topology from now on. So this is the Montgomery-Young problem case when this orbifold attains a structure of a normal projective surface. Well, this is the case, linear case, for example. So, and here the Kohler conjecture that let S be a Q-homology P2 with at worst quotient singularities. If the smooth part is simply connected, this means that this is M, say, that manifold with boundary. So this is simply connected. And S has at most 3 singular point. This means that D3 is equal to the conjectured bound for the exceptional orbits. So here, we haven't proved this conjecture in full version. So, but we are still we proved most cases, but we still left with one case. So if what if the condition replaced by the weaker condition? So this is weaker. Yeah. So the fundamental group is the commutator of this fundamental group is the homology group, and also this continuum is much tame. I mean, this is much difficult to handle in algebraic geometry. There are infinitely many examples, as with trivial homology group, but non-trivial fundamental group, and the number of singular points is 4. Well, these examples, you see, these examples doesn't violate this conjecture. It has 4 singular points, but fundamental group is non-trivial. But if we replace this condition by this, then we have to take care of these examples. So these examples obtained from the classification of surface quotient singularities by Briscoe. Okay, I'll stop here today. I'll go on tomorrow. Thank you.